So our first application of derivatives that we're going to look at is curve sketching. So we can take and we can look back at how did we graph things in the past, and how is calculus going to help us graph things that we already know how to graph, and then we can decide now, is our old technique better or is our new technique better? Plus, the new technique in calculus will help us graph functions that we didn't know how to graph. So that'll be a very powerful application, and we can learn it quite quickly. So first of all, if you had 3x squared plus 12x minus 1, what kind of graph is that? What shape of graph is that? It's a parabola. So how did you, in the past, graph parabolas? Must have been a very riveting experience that you remember so well. Do you remember that form of the equation? Now, if you had it in that form of the equation, it's nice because you could tell the vertex right away. But currently, ours is not in that form of the equation. How did we change it from what it looks like right now to this? Do you remember the name of the technique? Completing the square, yes. So we need to complete the square. This is our old technique. We do that by first factoring out the 3 out of the first 2 terms. Put those first 2 terms in brackets and left a space. Then we asked ourselves, what would have to go in that space in order for the brackets to be something that factors perfectly to a perfect square? We divided this number by 2 and squared it. Now, if I added 4 here, what have I actually done? I've actually added 12. So in order to compensate so we didn't do anything, we need to subtract 12. So then we change it in that form, and you would know that the vertex is at -2, -13. And since there's a 3 in front, you could go over 1, up 3, over 1, up 3, and graph your parabola. So that's our previous years for finding the vertex, completing the square. Okay? One thing that we're going to look at is how can calculus help us with this? If we want to find the vertex, which is right here, what does the derivative tell us? What is the derivative? What is the main thing that the derivative is? The derivative is the slope of a tangent, okay? Anywhere along the graph. So here we have a parabola. We could find the slope of the tangent anywhere along that graph. Now, if we're wanting to graph a parabola, what point's going to be the most helpful? The vertex. So now let's look at the vertex and let's think, well, if I drew a tangent right there at the vertex, what would that tangent look like? It'd be a flat line. Perfectly horizontal line. Can you see that that's the only point on our parabola that that's going to happen at? Because it's a minimum point that our tangent line is going to be completely flat. What do we know about a tangent line that's completely flat? The slope is 0. So now if our derivative finds us all of our tangent lines, and we're specifically interested in the one where the slope is 0, how is that going to help us? Well, let's take a look. How hard is it to take the derivative of this function? was pretty easy. And if we wanted the slope to be 0, how hard would it be to solve for x? You can probably see the answer already. Move the 12 over, divide by 6, and what do we get? -2. If you wanted to find the y-coordinate of the vertex, you just need now to plug -2 back into our original equation, and then you'd find -13. Pretty straightforward. So we can find the vertex even quicker now, perhaps, than our completing the square technique was in the past. The only thing we have to do now is wonder, well, how would I know that it's going up? Maybe we use our old technique of saying, well, the parabola has a positive a value, so I know it's going up, and I can go over 1, up 3, and use a bit of calculus and a bit of what I've learned before. We're going to also see that calculus can tell us more about the graph as well. So, if differential calculus is about the slopes of tangents, and these slopes tell us a lot about the graph, we've already talked about what does f prime of x equals 0 mean. That means that that slope is 0, and that tangent line would be horizontal. And this is going to be really important for graphing, because horizontal tangent lines only happen at maximums and minimums. And sometimes there's points called inflection points that we're going to learn about. That's sort of in the middle. But for the most part, right now, the key thing is that happens at maximums and minimum points. And in any function, those are key important points. Now, if you had a derivative greater than 0, what does that tell us about the slope? It just means that the slope would be positive. And if your derivative was less than 0, that means that your slopes would be negative. Now what's going to happen, I'm going to quickly go back to the one that we just did and just have a look at it. Okay? We noticed that it was equal to 0 at -2. And one thing we're going to do with curve sketching with calculus is we say, well, if it's equal to 0 at -2, what happens to the slopes before -2? So let's pick a number less than -2, maybe -4. And let's plug that in to our derivative and see what happens. If you plug in -4 for x, can you see that the derivative is going to be 6 times -4 plus 12? It's going to be -12. The derivative in this part, in this whole section, is going to be less than 0, which is negative. So one thing I just like to do, you can write f prime of x is less than 0, or you can just write a negative sign here to show that it's negative. Now, if our slopes are negative, and you can see them on the graph, can you see that any tangent that I draw on here is going to have a negative slope when it's less than -2? So what we're going to show with that is any time that your tangents are negative, your function's going to be decreasing from left to right. Does that make sense? Because in order for it to have a negative slope, your function has to be going down. And if we try a value bigger than -2, say 0, when you plug in 0, 6 times 0 plus 12 is positive. This section, your derivatives are all going to be bigger than 0. And we can show that just with a plus sign. And if we look at all these ones, it makes sense that all those slopes are positive. And any time that happens, our function's going to be increasing. So just looking at the derivative, we could have found the vertex, then determined, once we had that vertex, that from this side it would be decreasing, and after it would be increasing. And you would get your parabola from that as well. So it's important where we know where the slopes are positive, where the slopes are negative, and where they're equal to 0.